it's weird to have someone pronouncing my name correctly, so thank you very much. Okay, so today it will be a very astrophysical talk, and the idea is to describe the story, or at least a personal view of the story of supermassive black holes, starting from early times when they formed in protogalaxies up to now. And I will mainly focus on how we can distinguish between different models of mainly black hole formation and on models for the evolution of black hole spins using different observational constraints, mostly future constraints that we will get in the near future, hopefully. Okay, so just a couple of words of motivation for what I've been doing, well, since my PhD, basically. So here are two pictures of the same patch of the sky. One is observed in the optical band. This is the Hubble-Deep Field North, so it's basically the deepest, one of the deepest images of the sky that was ever taken. And here you see plenty of galaxies. Galaxies all the way to very high redshift, 5 or so on. On the right-hand side, you instead see the Chandra view of the same field. So here the image is taken in the X-rays. So while here in the optical image, you mainly see galaxies, all the galaxies. On the right-hand side, you see active galaxies, those that have a supermassive black hole in the center, which is accreting matter shining as a quasar. So the first thing that I think of when I see these pictures is that, well, there are many more normal galaxies than active galaxies. Okay, these two images are not the same depth, but this is true anyway. Typically, you have about one active galaxy every about 100 of normal galaxies. So a simple question that you can ask is it so because only few galaxies have a black hole in the center and this black hole is active at all times? Or on the other hand, basically all galaxies have a black hole, but this is active only for a short amount of time. So of course probably the truth is in between, but it's what I would like to see is what is changes from our theoretical view of black hole growth and what constraints we can get both from observing the sky in this way or in other bands, possibly not electromagnetic bands. A bit more of motivation in a sense of why describing all these problems in a cosmological context, which is what I typically do. Well, there was a campaign for observing black holes, so we know that black holes power quasar. This has been known since the 70s, more or less. But a picture of inactive black holes is much more recent. In fact, only in the last 10 years or so, we have had a demography of inactive black holes in the nearby universe. That's clearly difficult because to observe an inactive black hole, you have to detect the gravitational influence of this system, and this is easy in the Milky Way, in which the orbits of single stars can be observed in the center of the galaxy, and the black hole, and the potential that provides that shapes this orbit requires a dark object about 4 million solar masses in the center. So that's quite well known. Different techniques have been used for a bunch, about 40 galaxies in our neighborhood. And the masses of black holes, the orbits of stars in the center of these galaxies all suggest that they have black holes in the center. Supermassive black holes, so their mass is above 10 to the 6 or so. What is striking if you're interested into galaxy formation, galaxy evolution, and cosmology, is that the masses of these black holes correlate with the masses and velocity dispersion of the hosts. These are shown in these two plots. Here you see mass of the black hole as a function of mass of the bulge, observational point. You see this very nice correlation, almost basically a linear correlation. And here you have a correlation between black hole mass and velocity dispersion. So this all points to a coevolution. The two systems, black hole and galaxies, know about each other, and they must have grown somehow together. Well, first point to bring to think about is that black holes are hosted in galaxy bulges, so in the oldest and most central part of galaxies. So studies of the stellar populations of these bulges suggest that they are old, a few billion years old. So if black holes know about bulges, bulges know about black holes, and bulges are a few billion years old, well, it's expected that black holes are a few billion years old. So we are stepping into the realm of cosmology. The other thing the other observational point that we can think about is that quasars, so active black holes, have been observed all the way to redshift 6, actually 6.5, which corresponds to an age of the universe of less than 1 billion years. So about a tenth, even much actually less than a tenth of its age now. So we really have to go to the early phases of the structure formation to find out where these black holes were born. So let me, sure.
I'm sorry. Could you just say a word or two about how those quantities are measured?
Sure. So to measure the mass of the bulge, typically you use a dynamical modeling. So you measure the velocity dispersion. So the yes, here, exactly. The mass is basically velocity dispersion squared times the size of the galaxy, just standard physics. And the velocity, you measure the velocity dispersion by well, just observing the spectrum of this galaxy. From the way lines are broadened, you have an idea of how a random velocities goes. So you can get a measurement of the velocity. And the radius is just typically the half luminosity radius of the galaxy. So this is done using imaging. For the mass of the black hole, again, you use the same spectrum that gave you the velocity dispersion of the galaxy. But instead of using the integrated velocity dispersion, you find it as a function of radius. And is this a blackboard? Well, okay. So in principle, if this is the radius and this is the velocity dispersion, you can make a model of your own galaxy and suppose that the velocity dispersion goes something like this, something not particularly exciting. But if you see a strong rise in the center, that's a signature of some additional matter on top of the luminous matter that you see. So what they do is to take a set of orbits inside these potentials that reproduce this shape of the velocity dispersion, and the best fitting model gives you the mass distribution and the mass of the black hole. So it's not an exact science, but it's the best that they can do. And so for the velocity dispersion, it's the same over there. So you know, for astronomers, a factor of 2, a factor of 10 is okay. So we call this an amazing correlation. Yeah. We like log plots. So, okay, so all that said, let's now take a step back in time and try to understand, well, I will not describe how this correlation was established, but the time when galaxies and black holes were both young, and in which context, cosmological context, I will describe the evolution of black holes. So this is just a very simple reminder of what to expect. Well, we, in a cold dark matter universe with the parameters that WMAP found, we expect galaxies and structure to form in a so-called hierarchical or bottom-up way. So basically, after Big Bang, you had very small fluctuations. So some regions of the universe had a higher density, and so just the gravitational force within these structures made them attract more and more material surrounding them, until masses grew, and we started recognizing the type of masses that can be called proto-galaxies and later on galaxies. So this is a very short summary, but this can be seen in cosmological simulations. So you see how going from high redshift to low redshift, so from early times to now, the structures are growing by accreting the surrounding envelopes, the surrounding material. So what should be, and you see here that at this point, all the material at the beginning was spread out, is condensed into a very, very small number of blobs, which are basically the halos of the galaxies that we see today. In this hierarchical picture, the first galaxies, the first proto-galaxies, were very small, and systems like a Milky Way or cluster of galaxies formed later on when enough mass had collected all together. So this adds a little complication to what we actually call a galaxy. So in the very small little regions that were collapsing at the beginning, most of them could not be called proto-galaxies because they had only dark matter but no luminous matter in the center. The reason is that to go from a halo with some dark matter and gas to what we could call a proto-galaxy, so a system with producing light, with stars and eventually a black hole, you need to take the gas that you have in this proto-galaxy, in this halo which is flying around, and let it cool down until it reaches temperatures and densities at which stars can form. And the same requirement that gas cools down must be asked to form a black hole, and we will see that in a minute. So in this picture of this hierarchical world, at very early times, so if, I just think of it as 10 to the 7, 10 to the 8 years after the Big Bang, only very, very few halos, very few systems in a cosmological volume had the capability of gas cooling in the center. And these were the most massive halos at the time. Now, if you think of the Milky Way today, about, considering all gas, stars, dark matter, a mass of about 10 to 12 solar masses, the typical halo that could host star formation at these higher redshifts is of order of 10 to the 5, 10 to the 6 solar masses. So you can just imagine how many of these systems you need to form a galaxy today. So from now until when I talk about black hole formation in proto-galaxies, you have to imagine these very small halos, a million solar masses, made of basically dark matter and gas in it, let's say about 10%, 14% in gas. And we will examine what happens to this gas that has to do with black hole formation. So this is the setup. Now let's see what can happen in these sort of proto-galaxies, in these rare proto-galaxies. Remember they are rare, so you don't form stars and black holes basically everywhere at the beginning. So this is a cartoon that is borrowed from an old paper by Martin Rees. Basically in the 80s, most of the physical processes that we expect have formed black holes were already known. So basically now we keep on studying the same cartoon, trying to put some more details on each of these roles. So here you see that the idea is that you start from a gas cloud that I call proto-galaxy in my lingo, and using and through various processes you form a massive black hole. I will not focus on all these processes. That would be more a lecture than a class that I teach, rather than a talk. And I will focus only on a couple of systems. So basically what I'm trying to show is that that different physical phenomena can form black holes. These will have different histories in the universe, and what I'm trying to find are techniques to distinguish between these. So basically I want to understand how black holes formed in the first place. So you see here that I divided the slide in two parts. So basically, I will focus on two different ways of forming black holes. One that forms light black holes, a few hundred solar masses. So for supermassive black holes is very small. And one that forms more massive black holes of up to about 1 million solar masses. So remember that this happens in these protogalaxies, very small protogalaxies. So in this case, you form black holes which basically use up most of the gas that form the protogalaxy itself. So in the first case, we can expect that black holes just follow from the standard path of stellar evolution. I mean, we all know that stellar mass black holes are the end point of the life of massive stars. Now, bring the stars to very, very large masses, well, you end up forming very, very large black holes. If I tell you now of masses of stars of a few hundred solar masses, you might think that this is quite uncommon. But this is the typical mass expected for the first generation of stars that formed before the universe was enriched in metals. This is due to the different type of cooling that happens when metals are not round. Basically, the only coolant is hydrogen, either in atomic or molecular form, which is not an efficient coolant, and this leads to very little fragmentation and very massive stars. And simulations of the collapse of these stars suggest that if the mass of the star is very, very large, larger than about 150 solar masses, the fate of this star is the collapse, direct collapse into a black hole with very tiny mass loss, so a few hundred masses. So this is a nice story, although we don't have proof that the first stars formed exactly in this way and had the right range of masses for forming black holes. Note that if the mass of the stars is not above this 250 solar masses limit, the final fate.
So how long does it take for those
10 to 4 to 5 years. It's a very rapid process, according to simulations. I mean, well, sure, the lifetime, the mass is very large, so the lifetime is not expected to be short. But we don't have a complete simulation from birth to death of these stars. So yes, and the other point that I wanted to make is that if the mass of the star is just below this limit, the final fate is not the formation of a black hole at all. It's the complete explosion of a star with no remnant. So it's very important to understand if this limit really exists and if it is feasible. Okay, so a second way of forming a black hole in these protogalaxies is to skip the star formation part and to find a way of dumping a lot of gas in the center of these protogalaxies, and this has to be a very efficient process fighting against star formation. Just think of this halo. So you want to dump a lot of gas in the center, basically within its Schwarzschild radius for forming a black hole. So you're trying to use up as much gas as possible in a very efficient way to go to a black hole. And now suppose that within this protogalaxy a supernova explodes. Well, you're doomed. At that point, you lose all the gas that you made a big effort to condense. So basically, if you want to form a black hole by these processes which are called direct collapse, you have to be very efficient in compressing your gas before stars actually form. So suppose that we take these two models, we take cosmological volume, we consider all the protogalaxies that are around, and we check them for conditions that would allow black hole formation. So not all galaxies are prone to black hole formation according to the systems. You have to select them according to their angular momentum, according to their temperatures and masses. So if you do this little exercise, and I'm telling you about a kind of a black box now, but I can give you more details if you want, you end up predicting some mass functions for the initial population of black holes that are shown over here. So here I just took some, how can I say, very different models, so some extremes, just to show you how sensible assumptions, plausible assumptions on black holes formation can lead to different mass functions and different evolutions, and we will see how they can differ later on in time as well. So here it's just the mass function, so the number of black holes is a function of mass in a cosmological volume, so this is actually a density. So here, this magenta line shows something that I typically call a low-efficiency direct collapse. So you form not that many black holes, about 0.1 per megaparsec cube, with a typical mass about 10 to the 5 solar masses. So in terms of the typical masses that are around, these are huge. On the other hand, they don't happen very, very often. The green line shows a high-efficiency direct collapse model. So in this case, you form plenty of very massive black holes. Here, almost 1 per megaparsec cube, again with a mass of about 10 to the 5 solar masses. So you might expect, I mean, thinking of the comparison between the Chandra and the Hubble space images, that this green model will probably lead to a lot of quasars with very short lifetimes, and this model probably to a few quasars with a longer lifetime. And here, as a comparison with the black histogram, is a mass function that assumes that porphyry star remnants are the seed of black holes. So note how here the mass function is peaked at about a few hundred solar masses. So a very large difference with respect to the previous models. So now let's start from these systems, from these three different mass functions, and let's evolve them in time and down to now and see what happens to these systems. Okay, so this is just a picture of the technique that I use for that, or how to describe the situation. So remember the simulation that I showed with all these galaxies merging together? You can take different snapshots as a function of time and reconstruct what happened, which galaxy merged with which else, ending up forming a galaxy today. So you start with something today, Milky Way, and you trace its history back in time all the way to very high redshift. Notice here that within these white circles, which are my galaxies, there are black points. These are the black holes. So I start from the galaxies with black holes at very high redshift, and I follow the history of these black holes in galaxies all the way to today. What do I have to study for this? Well, at minimum, you have to understand, or you have to include somehow the processes that make black holes bigger from a few hundred or a few thousand solar masses. So, of course, black hole mergers and gas accretion. So, black hole mergers are expected to happen in this hierarchical system, a model in which basically galaxies keep on merging one with the other. And if you include mergers only, you start from small black holes and you build up big black holes just by summing them up. So in some sense, you are keeping the total mass density of black holes in the universe fixed, and you change just the shape of the mass function. On the right-hand side, you have the typical what we call a quasar, a black hole which is accreting mass from an external gas disk, shining as a quasar, and the addition of material onto this black hole will make it bigger. So at this point, if we include also accretion in our models, we're changing both the shape of the mass function but also the normalization. And so you start from your small black holes at high redshift. Here you see a typical example. And the mass grows through these processes, accretion and merger, down to redshift 0. So here in this plot, you see this these basically exponential growth phases, which is when the black holes are quasars. And you see here these dots, which show when black holes merge. So in principle, just looking at this picture, it seems plausible to say that accretion rather than mergers contribute most to grow black hole masses. And here is an example of what we can compare models to. So now take all the quasars in the universe. We observe them. So if you integrate the luminosity function of quasars, so the number of quasars, number density of quasars per unit luminosity, if you integrate over all luminosities and all times, you get the total energy density that was emitted by quasars in the whole lifetime of the universe. Now, if you have an energy density, and energy is the radio efficiency times mc squared, well, if you assume a parameter, this is parameter derivative efficiency, epsilon, you can convert the energy density into a mass density, which is the total mass density that contributes to growing black holes. And here it is. So this blue hatched area shows the type of constraints that we get from the observed luminosity function of quasars. And here we have the three models that I was showing at the beginning. So in principle, this green line shows a very high efficiency, large seed models for black holes, which predicts that basically black holes have been creating like crazy for a long time, and they're basically off the observation constraints. While the other two models, the low efficiency direct collapse or pop-free star remnants, are within the expected range. Note that the expected range is quite large. We were mentioning before about factors of 2 orders of magnitude. So there is a lot of work to be done before we can constrain the evolution of black holes. So this is just another simple outcome of these models, just to show you what we can predict and what we can measure now. So this is the mass function of black holes again, but not of seed black holes at the beginning of the universe, but of black holes now at redshift 0. So again, the same three models: low efficiency, high efficiency, pop-free stars. The models are the histograms with error bars. Someone may notice that there are errors on the theory, but not errors on the observations, which are these lines. Well, at least I put errors on my work, so it's, I think, sensible. Anyway, so these lines show two different mass functions for black holes. Notice that the observed part, is basically down up to the knee. Beyond the knee, so for masses below about 10 to the 7 solar masses, everything is an extrapolation. So what can we say? Well, basically what we can say is that with current observations, we cannot tell much about the prehistory of the black holes, because where models differ is where we don't have data. So we need more details. So this is just saying the same, so everything in extrapolation. So we need more data, and what I say typically is that we need a census of inactive black holes. So let me just show you what, in principle, I would like to know. So this plot shows, again, the same three models: low efficiency, high efficiency, pop-free stars, compared to the data that we have on black holes now. Here, the same two correlations between black hole mass and velocity dispersion that I was showing at the beginning. Everything we know goes down to here. So the range of black hole masses that we really want to probe is between 10 to the 5 and 10 to the 6 solar masses, where the data is basically extremely rare. One of the few black holes in this mass range is actually a Milky Way one. A very powerful diagnostic would be the occupation fraction of black holes, which is shown at the top. Actually, here what I show is the fraction of galaxies at the given velocity dispersion, so basically at the given mass, that have or not have a black hole. So you see here that at very low masses, we expect that the three models differ quite a lot in the occupation fraction of black holes. But the problem is that what we need here is to know how many galaxies have or not a black hole, not an AGN. Having an AGN, the occupation fraction of AGN would just be a lower limit of occupation fraction of black holes. Okay, so this is basically what we need. The second, I would like to argue for a few minutes, although I'm running late, that there is another information that someone like me would like to have. I mean, we know that black holes have masses, and I've talked about masses up to now, but black holes also have spin. And what is the typical spin of black holes is of importance for us. Well, first of all, because it determines this radiative efficiency, this parameter epsilon, that goes into converting the energy density into a mass density. So we're trying to constrain the masses of black holes using this parameter, but then we don't know these parameters if we don't know the spins of black holes. So we're in a sort of vicious circle. So if we can constrain at least one of the two, we're in a better shape. And the black hole spin is also important for understanding how possibly jets coming from black holes are formed, possibly by the Blunt-Worth-Naik mechanism, for example. Is spin really important for energy extraction from the black hole? Well, so these are all questions that I have, and I think would talking about black hole spins can again be a fit into this picture of black holes' growth in a cosmological universe. So we have seen that black holes grow in mass by mergers and accretion, while also black hole spins evolve by mergers and accretion. So if we consider mergers, black hole mergers, they influence the evolution of black hole spins. But if you think of it, it's a sort of a random. You can imagine the influence of mergers on black hole spins as a sort of random walk. A black hole merges with something else. A smaller black hole, the spin goes a bit down. Then it merges with a black hole of the same size, and the spin goes up. And basically, it keeps on fluctuating depending on a few parameters that I will discuss in the following. Basically, the evolution of spins because of mergers will depend mainly on the mass ratio of the two merging systems and on the orbital parameters. Now, but black holes mostly grow in mass during their evolution by accretion. So probably accretion will play an important role in determining also the spin of black holes. And this is particularly true if we consider accretion via as from a simple thin disk. In this case, in just 10 to the 7, 10 to the 8 years, you take a Schwarzschild black hole and you spin it to more than 0.9. So spin up by accretion. So in many ways, you can see accretion as like you can see, not rigorously, as a long series of mergers, but all with the same angular momentum, basically. You keep on kicking the central black hole in the same way. So it's clear why you're spinning up this system. So if black holes grow mostly by accretion, probably that's what influences most the situation. So I will probably skip this slide. But Emmanuel is here. He did this plot so he can give you more details. And I will just show you how different stories of black holes can lead to different spins. So again, we need measurements of spins to understand how black holes grew. So at the moment, let's just pretend somehow that black holes grow only by mergers. Accretion doesn't influence spins. And take all the black holes in my models and let them change in mass and in spin because of mergers. So this is a plot that shows the distribution of spins. So this is the number of systems as a function of the spin, in which I assume that basically you start from all black holes with very slow spin, and let them grow by mergers. And what happens? So this is distribution of black hole spins before mergers, and this distribution of spins after mergers. So you don't have to look at all three panels, just focus on one and it will be fine. So what happens here is that typically mergers spin up black holes. So you end up growing a population of black holes that have a larger spins. But, as I was mentioning at the beginning, not all black holes merge in their lifetimes. Accretion typically happens on 90-something percent of black holes, but only half of the black holes that we see now in galaxies experience a merger in their lifetime. So what happens in the end is that the distribution of black hole spins looks very much like the distribution of spins before merger. So mergers only retain the memory of initial conditions. So if we measure a distribution of spins which is skewed towards, well, when the distribution is kind of flat, that's a signature of accretion being not influent for black hole spins. Now, what happens instead if we consider instead that black holes grow in mass by accretion? They are surrounded by this for a large fraction of their lifetime, probably. They accrete material with the same angular momentum, which is very plausible. And what happens? Well, they are spun up very soon. So here, I assume that black holes actually start all with spin 0. And then I took a snapshot of these black holes after about 1 billion years from the beginning of the universe. And already, we see that most of them are rapidly rotating. So you see here that the spin distribution peaks at about 0.9. Okay, so this is the distribution actually of black holes before mergers. So what I'm showing here is what the distribution that would be detected by crystal by gravitational waves if the spins of black holes during the spiral can be seen. Now, what happens if you can measure the spin of black holes during the ring down? Well, you find probably a different distribution. At this point, while before, if accretion was not spinning up black holes, mergers tended to spin up black holes. Now, if you have a distribution of spins which is basically peaked at the maximum value, mergers will spin down black holes, or at least a bit. So in this case, you would measure very different distributions for black holes spins before and after mergers. Now finally, if you can measure the whole distribution of black hole spins, and in this case, it's, for example, if you use the spectral features in AGN, or extreme mass separation in spirals, but I will go back to this later. The distribution of spins that you would expect is something like this. So again, since not all black holes experience a merger in their lifetime, most of the black holes retain a memory of the peak of distribution for accreting black holes will be about 0.9. So this is just to show that to understand the growth of black holes via mergers and accretion and their evolution from a population of SIDS, we can use different techniques. We can measure the masses of black holes in small galaxies to understand how they formed. We can measure the luminosity function of quasars to understand how they grew. And we can measure black hole spins to understand what type of accretion properties and what type of merger properties we had. So I will also, since you said that 5 we have to leave. Okay. Well. Okay. So the last model that I want to present is something which is called the chaotic accretion. So what happens if? What happens if accretion, instead of spinning up black holes, spins them down? Okay, this might seem a very controversial sentence, and I think it's very. This is not my favorite model. But what happens if black holes grow in mass by very short accretion episodes that happen basically on isotropic orbits? So every time a little packet of material is accreted, it changes a bit the spin of the black hole. Since Since spin down is easier than spin up, and this is just due to the value of the angular momentum at the last stable orbit for in case of retrograde or prograde orbits. If you have accretion happening in this weird, chaotic way, what you end up predicting is a population of black holes that basically don't spin. So in this case, mergers would be the main way to try to give black holes at least a little spin. But the main population will be dominated by these Schwarzschild black holes that keep on accreting matter from different orbits. So again, these are three extreme models, but very simple measurements of black hole spins, mainly for the whole population, can give very, very important details on how accretion happened. If it is through the standard picture that we have of black holes doubling in mass when they are quasars, or through this, let's say, alternative model of chaotic accretion. Okay, so I've told you the whole story. We started from the few million years after the Big Bang, and we reached inertial zero. So let me just summarize what, in principle, would be my wish list. Well, first, how and when black holes accrete mass. Well, it's not first, it's a random order, really. How and when black holes merge, how and when black holes form, and finally, how fast they spin. So, with different observational signatures, we can constrain different questions. So I showed you how detecting the masses or that there is no black hole in small galaxies can help understand how and when black holes form. Detecting the spin of black holes can tell us a lot also how and when black holes accrete mass. So all these questions are interrelated and could be addressed at the same time, should be addressed at the same time. So what are the type of techniques that we can use to detect this? One is the standard electromagnetic radiation. So these are two very interesting cases. So this is the Chandra Deep Field, so the deepest X-ray image ever taken. You see here how many active systems you have. So studying the Chandra Deep Field could, in principle, lead to detections of black holes, accreting black holes, quasars, up to redshift 4 to 6. So very close to the ages when black holes form, at least in time. These other cases, NG6 6240, it's one of the very, very few cases of double AGN ever observed, double or binary, which are probably so rare, not because they're not there, but because they're obscured by dust. So if you have an active black hole, a quasar, but you have a lot of star formation around it, which is very typical during mergers, you end up obscuring the central part, so you don't see the two black holes in this merging system as, well, a binary. So since we discussed how in this hierarchical universe galaxies merge, black holes merge in the center, how can we check the merger rate of these systems if they're mostly obscured? Sure, you can observe some of them in the X-rays, but you need very high resolution and in the hard band, which is quite difficult except with Chandra. So anyway, these type of observations give a lot of information on how black holes accreted mass because they are quasars while they accrete. And studies of both the Chandra field of nearby systems can also give constraints on the spins via integral systems, really. Or for very close by systems, if you observe the shape of the spectrum of this AGN, you might get some hints on the spins. For example, by the gravitational redshift of some spectral lines that change shape if they are produced very close to the ISCOS, to the last stable orbit. A second way of detecting black holes is, of course, by gravitational waves. So in this case, you don't use the standard techniques that astronomers use, so looking at light, but you have to decode the emission from of gravitational radiation from systems. And here I divided these two cases, so massive binaries and M-rays, and I will just discuss which of the signatures that I discussed each of those can address. So massive binaries, so black holes merging, massive black holes merging. They are basically cosmological probes, so they will address in my wish list when and how black holes formed. These massive binaries, at least for the for LISA, the Laser Interferometer Space Antenna, these are very loud systems that can be detected at very high redshift, basically when they were forming. But they represent a biased population. They're only merging black holes. And they are about 50%, 40 to 50% of the black holes that we ever had in the universe. So if we want a complete synthesis, so this would be my perfect probe for understanding how black holes formed. But to have this census of all the black holes and their spins, we think that an easier way would be to use these extreme mass relation spirals, so a compact object, stellar mass black hole or neutron star that spirals towards a central black hole. And in this case, they are not extreme probes in terms of cosmology. They cannot probe all the way to redshift 20 or 30, so when the galaxies and black holes formed, but still they can probe black holes to redshift of order of 2. And they would provide an unbiased biased picture of the black hole population. So a combination of the various techniques, electromagnetic band, massive binaries detected in gravitational waves, and extreme mass relation spirals again in gravitational waves will provide answers to my complete wish list. So let me just show you what type of differences we expect in these cases. So here it's another plot that Emanuele made, in which he shows the signal-to-noise ratio that we expect in the case of LISA for merging black holes as a function at different redshifts, here from redshift 0.54 to redshift 10, as a function of the mass of the systems. So here you have very high signal-to-noise ratios up to redshift 10. Redshift 10 is much less than a billion years after a Big Bang. So at that time, most of the black holes that were around were still in their original state. They haven't changed much in mass. So these high redshift probes can tell us the differences. Now, you might ask, okay, sure, but so how much different are the models that you have described to us? Well, they predict very, very different merger rates, very, very different histories for black hole mergers. This is a simple plot of the merger rate of black holes as a function of redshift. Actually, this is the merger rate that an observer at redshift 0, so on Earth, will observe. And here are some of these models that I was showing before. So do you remember 3 mass functions for low efficiency for seed formation, high efficiency seed formation, and pulp-free star remnants? They are still here. So the high efficiency model is actually shown here with a dotted line. The pulp-free star remnants are shown with a solid line, and the low efficiency model, the one that was before in the plots before, is shown here. So in practice, different models can predict different a merger rate of massive boundaries that varies by about 2 orders of magnitude. So in principle, we expect that this would be an easy probe for detecting the formation of black holes. And so here I will just leave you with what instead MRIs can do for us. So MRIs, I think that everybody knows here, are these compact objects falling into a large black hole. So they don't have a high signal-to-noise ratio for detection of gravitational waves. But if you integrate long enough, they can give us information. So this is a plot that Jonathan Gare put together. And it considers the history of black holes based on this merger and accretion scenario, starting from now and going back in time. So, for example, take this black hole over here, and this is a mass very similar to the black hole in the Milky Way. So you take this black hole, and you can trace its mass growth back in time. So here it's redshift 0 now. So this is redshift about 2, 2.5. And you can trace the time of its growth that can be detected via this MRI technique. So, for example, for this black hole, which is actually a bit larger than the black hole in the Milky Way, you can trace its history down to redshift 0.5. But for a smaller black hole, actually these are the black holes that will tell you a lot about the mass function that we don't know about. You can trace the history all the way to redshift 2.5. So now, take all the black holes that you observe nowadays, the mass function of black holes, and try this exercise. So take all the mass function today and evolve it back in time, and try to find out how many of these systems you expect that can be detected with this MRI technique. Now, would different mass functions be different in the eyes of these MRIs? Well, indeed they would be. So this is just a simple example. This is still work in progress, in which the distribution of detections for MRIs is shown as a function of the black hole masses. And here, what is shown is basically a difference between two mass functions of black holes today. So what I was showing before, so in one case, so if you have the mass function, at the moment, from the observational point of view, we don't know if the mass function is steep at the low masses, below 10 to the 7, or it's flat. So using the flat or steep mass functions, you will get these two different curves. And that would help understanding how many black holes, small black holes, we have over here. So this is just a summary. I've discussed basically how you can form black holes in a cosmological context, and how they grow in time by mergers and accretion, and how the models differ in various parts of the mass function, of the spin distribution, and how we have signatures that can tell us the differences between these models. I mean, I'm a theorist, so I am intrigued by just the idea of learning how black holes were formed in the first place. And there is a wide range of probes that can distinguish between these models, and probably in the near or near far future, we will learn much more about black holes. Thank you.